Hello, welcome to the first video for Chapter 3. This section dives into probability, which we'll be focusing on for a while. This is getting you ready for the real math of statistics we'll be doing in Chapter 4. Learning terminology and really getting a grasp of some of the basic concepts of probability are our main goals this section. Alright, let's get going. Hi everyone, welcome to the video for Chapter 3, Section 1. In the first two chapters, we focused on collecting and describing data with the ultimate goal of writing summaries, drawing conclusions, and making decisions. It may seem like we're going in a completely different direction with this chapter, but one important concept in analyzing our results is being able to determine accuracy and minimizing the chance of receiving a false result. And therein lies the focus for this chapter, chance. We're going to narrow down our concentration a little bit and study the probability of certain results or observations actually occurring. In particular, we're going to learn how to identify a sample space for a probability experiment and how to identify simple events, use the fundamental counting principle, recognize the difference between classical, empirical, and subjective probability, find the probability of the complement of an event, and construct tree diagrams. This first section is not overly formula heavy, but there is a lot of vocabulary to digest, so don't be afraid to pause or rewind the video to take good notes for yourself. Let's start with some basic terminology. A probability experiment is any repeated action or trial through which results such as counts, measurements, or responses are obtained. For example, rolling a fair six-sided die. The action is easy to repeat and specific results are recorded each time the trial is completed. The result of a single trial of a probability experiment is called an outcome. For example, 3 is one possible outcome in the probability experiment of rolling a die. The set of all possible outcomes for probability experiment is called sample space. And you'll notice in this example, we do use proper set notation to denote sample spaces, with braces to begin and end and commas to separate the elements. Here's the sample space for the probability experiment of rolling the die 1 through 6. When we're concerned with one or more outcomes in the sample space, a subset, then we call that collection an event. Typically, events are subsets in which the outcomes share some kind of characteristic. So, for example, rolling an even number is an event consisting of the outcomes 2, 4, and 6 only. This is a subset of the sample space as it does not contain all of the elements of the sample space, and these particular outcomes share a common characteristic, that they are all even. Let's practice using some of this terminology. A probability experiment consists of tossing a coin and then rolling a six-sided die. Pause the video and see if you can describe the sample space. There are two possible outcomes when tossing a coin, head or tails. For each of these, there are 6 possible outcomes when rolling the die, 1, 2, 3, 4, 5, or 6. So one way to list the outcomes for actions occurring in sequence is to use a tree diagram. As you can probably imagine, tree diagrams can get very involved when there are lots of outcomes and combinations. But if we follow the tree diagram through each coin outcome, heads here on the left and tails on the right, and the possible rolls of the die below, we see that the sample space has 12 possible outcomes in all. Our sample space could be written in set notation like this. Notice again the braces to begin and end the set and commas to separate the individual outcomes. We can further classify events into a subcategory known as simple events. Simple events are those that consist of a single outcome. For example, the event of tossing heads and rolling a 3 only has one outcome in it. That makes it a simple event. An event that clearly has more than one outcome is not a simple event, like tossing heads and rolling an even number. There are 3 possible outcomes in that event, which makes it not a simple event. So let's practice this. Determine whether the event is simple or not. Number 1, for quality assurance, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. Number 2, you roll a six-sided die. Event B is rolling at least a 4. Pause the video and see if you can figure out which event is simple and which event is not simple. Event A only has one outcome, choosing that one specific machine part that is defective. So event A is a simple event. Event B, on the other hand, has 3 outcomes. Rolling a 4, 5, or 6 is rolling at least a 4, so event B is not a simple event. Okay, now that we've got some basic language down, let's start talking about the different classifications of probability. The first one is probably the one that you are the most familiar with. It's called classical probability, or some call it theoretical probability. It assumes that each outcome in a sample space is equally likely to happen, and it says that the probability of some event occurring within that sample space is equal to the number of outcomes in the event divided by the total number of outcomes in the sample space. Notice the notation here. It kind of looks like a function notation. This is not a product. We're not multiplying P times E. This means literally the probability of event E. That's how you read that notation. Let's do a couple of classical probability problems. Let's suppose the probability experiment you're conducting is rolling a 6-sided die, and then number 1, event A is rolling a 3. Number 2, event B is rolling a 7. And number 3, event C is rolling a number less than 5. Pause the video and see if you can find the probability of each event. To figure out any of these probabilities, we need to first know what's in this sample space. The sample space for this probability experiment is the set of numbers 1, 2, 3, 4, 5, and 6. So for number 1, to find the probability of event A, we need to count up the number of ways that event A can happen and divide that by the total number of objects that are in the sample space. Well, there's only one way that event A can happen, by rolling a 3. So we say the probability of rolling a 3 is 1 divided by the total number of objects in the sample space, which is 6. So 1/6, or approximately 0.167. And number 2, event B, there are 0 outcomes that fall in the event of rolling a 7 because it's not possible for a 6-sided die to roll a 7. So the probability is 0. Number 3, event C, is rolling a number less than 5. Well, there are 4 ways for this event to happen. We could roll a 1, 2, 3, or 4. So the probability of rolling a number less than 5 is 4 out of 6, or about 0.667. Okay, let's try a problem that's a little bit more complicated. Assuming an equal chance of getting a heads or a tails in a toss, you roll 4 coins, keeping track of the order in which you toss them. What is the probability of having 2 heads and 2 tails in a group of 4 coins? Pause the video and see if you can come up with a sample space pertaining to this probability experiment. Once you have the sample space, count up the number of ways you can have 2 heads and 2 tails in a group of 4 coins. One of the challenges many students have with studying probability is knowing when to trust intuition and when to back away from it. Many students would answer this question with a 50% chance, but that's actually not the solution. This problem is a good example of the importance of looking at the total number of outcomes. That is, really understanding what's in the sample space. If we wanted to write out the sample space by hand, it might look something like this. There are technically 5 possible scenarios our group of 4 coins could fall under. All 4 heads, 3 heads and 1 tail, 2 heads and 2 tails, 1 heads and 3 tails, and all 4 tails. Then, within each of these scenarios, we have to think about all the possible combinations of heads and tails. For example, in the scenario of having 1 head and 3 tails, saying that the first coin is a head versus the last coin is a heads gives us 2 entirely different makeups, and we have to consider both of them. We need to consider all possible combinations. In doing so, it turns out that our sample space has 16 possible outcomes total. So, to find the probability of having 2 heads and 2 tails, we need to count up all the combinations that fall in that scenario. There are 6 ways of having 2 heads and 2 tails in a 4-coin group, so our probability ends up being 6 out of 16, or 6 divided by 16, which is about 0.357. The hardest part about problems like this is just coming up with a sample space. If we had missed one combination, the denominator of our probability would be off, and then our calculation could be wrong. There's another way to visualize the possible outcomes of a probability experiment. It's called a tree diagram. We briefly went over one in the coin problem, but let's look at one a little bit more closely. So for instance, let's say you're purchasing a new car. The possible manufacturers, car sizes, and color are listed in the table. How many different ways can you select one manufacturer, one car size, and one color? Create a tree diagram to represent the different possibilities. Well, you start by picking one of the categories. Let's do manufacturers. So we could choose a Ford, a GM, or a Honda, and then you basically create branches like a tree for all of your possibilities beyond that. We could further narrow down our choice by selecting a compact or mid-size. So we draw smaller branches from each of the manufacturers to those choices. Then from there, the last category of color. You make still smaller branches to denote each of those under the compact and mid-size choices. Pause the video and take a moment to fill in the tree diagram for all the possibilities for this experiment. You can abbreviate the colors the way they have in the table, W for white, R for red, and so on. If we wanted to create a tree diagram for this problem, here's what it might look like. Okay, this is still a lot of work. Isn't there an easier way? Why, yes, there is. It's called the fundamental counting principle, and it works like this. If one event can occur in m ways, and a second event can occur in n ways, the number of ways the two events can occur in sequence is m times n. This can be extended for any number of events occurring in sequence. So if we wanted to do this for the last example, we know that there are three choices that we're making. The first one was a choice between three manufacturers. The second was a choice between two car sizes. Then the third was a choice between four colors. So according to the fundamental counting principle, we can now say 3 times 2 times 4 equals 24 possible combinations. Much easier than trying to list out what was in the sample space. Let's do a few more examples using the fundamental counting principle. The access code for a car security system consists of 4 digits. Each digit can be any number from 0 through 9. How many access codes are possible when, number 1, each digit can only be used once and not repeated, 2, each digit can be repeated, or 3, each digit can be repeated but the first digit cannot be 0 or 1. Pause the video and see if you can use the fundamental counting principle to solve these problems. Here's the solution for number 1. Because each digit can only be used once, there are 10 choices for the first digit. Then there are only 9 choices left for the second digit, 8 choices left for the third digit, and 7 choices left for the fourth digit. Using the fundamental counting principle, you can conclude that there are 10 times 9 times 8 times 7 equals 5,040 possible access codes. Okay, how about number 2? Because each digit can be repeated, this one's a little simpler. There are 10 choices for each of the 4 digits. So there are 10 times 10 times 10 times 10, or 10 to the 4th power, or 10,000 possible access codes. And finally, number 3. Because the first digit cannot be 0 or 1, the trick for this one is to limit the number of ways the first digit can occur. That means there's only 8 choices for the first digit, but there are still 10 digits available for the second, third, and fourth digits. So there are 8 times 10 times 10 times 10, or 8,000 possible access codes. Okay, I think we're ready for the next type of probability. It is called empirical probability, or some call it relative frequency or statistical probability. The important thing to remember for this one is that this type of probability is based off of observation of historical data. Empirical probability is empirical or based on experiment. This is the type of probability that is based on repeating a probability experiment over and over, and it is found by dividing the frequency of the event, or how many times it happened when you experimented, by the total number of observations. That is F divided by N, the frequency divided by the sample size. Here's an example involving empirical probability. A company is conducting a survey of randomly selected U.S. adults to determine how they read books during the past year, if at all. So far, 1,502 adults have been surveyed. The pie chart shows the results. Note that digital books include e-books as well as audiobooks. What is the probability that the next adult surveyed read only print books during the last year? The event is a response of read only print books. The frequency of this event is 560. The total of the frequencies is all the frequencies added together, which is 1502. The empirical probability that the response of the next adult is read-only print books is 560 divided by 1502, which is about 0.373. It turns out that there's an interesting connection between classical probability and empirical probability. It's called the law of large numbers. It says that as an experiment is repeated over and over, the relative frequency recorded for the event, in other words, the empirical probability, approaches the theoretical probability of the event. For example, consider the simple probability experiment of flipping one coin. If you were to flip that coin 10 times, even though the classical method says the probability of each outcome here is 50%, would you honestly expect 5 of those flips to come up heads and exactly 5 to come up tails? Probably not. There's just too much variation in what we call the short run of this experiment. But the law of large numbers says that as you repeatedly flip a coin, the actual proportion of heads and tails will eventually even out to approximately 50-50. But we're talking over the long haul, hundreds to thousands of repetitions of these trials for this probability experiment. Okay, now the third type of probability really is the easiest. It is subjective probability, and it just refers to your best guess, kind of like a gut estimate. This would be like a doctor saying that a patient has a 90% chance of full recovery. He's not quoting a hard, fast statistic, but he's probably thinking about common, perhaps minor complications that may keep the recovery rate from being a guaranteed 100%. So, with these three types of probability in mind, let's practice identifying the type being used in the following examples. Classify the statement as an example of classical, empirical, or subjective probability. Number 1, the probability that you will get an A on your next test is 0.9. This sounds like an educated guess, so it's subjective probability. Number 2, the probability that a voter chosen at random will be younger than 35 years old is 0.3. This statement is most likely based on historical survey data or voting records. That makes it an empirical probability. And you can probably guess the last. Number 3, the probability of winning a 1,000-ticket raffle with one ticket is 1/1,000th. Assuming that all the tickets are equally likely to be drawn, and knowing the raffle has exactly 1,000 tickets, this probability is classical, 1 out of 1,000. Let's practice using the fundamental counting principle one more time to make sure we understand how it works. Your college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What is the probability of getting your college identification number when randomly generating 8 digits? Pause the video and see if you can come up with a solution using either classical, empirical, or subjective probability. There are a few key points to keep in mind when solving this problem. Each digit can be repeated. There are 10 choices for each of the 8 digits. Using the fundamental counting principle, there are 10 times 10 times 10 times 10 times 10 times 10, and so on, or 10 to the 8th, or 100 million possible identification numbers. Only one of those numbers corresponds to your ID number. Now think about what the question was. The question was, what's the probability of getting your ID number when randomly generating 8 digits? So it's not just this big long number. That is how many possibilities there are. The question was about getting your number out of that total. So the probability of getting your number is 1 in 100 million. Very slim possibility. Okay, we'll end this section with a few big picture concepts. In general, no matter what the probability experiment, the probability of an event is bound between 0 and 1 inclusively, meaning the probability of any event can be 0 or 1 or any fractional value in between. A probability of 0 means it's absolutely never going to happen, and the closer you get to a probability of 0, the less and less likely it will happen. Right in the middle, a probability of 0.5 means there's an even chance either way, and a probability of 1 means that it is absolutely certain to happen. Obviously, the closer you get to a probability of 1, the more and more likely it is to happen. Because of this range rule for probabilities, it's fairly easy to calculate the probability that something does not happen if you already know the probability that it will happen. It's called the complement rule. The complement of an event E is the set of all outcomes outside of event E that are still part of the sample space. In the Venn diagram, the outcomes pertaining to event E would be inside the pink circle, while all the other outcomes not included in the event, but still part of the sample space, would be in that beige area outside of the circle, but still within the borders of the rectangle. This beige area is what we call the complement of E. So if I represent the event with E, then the complement is often written E with a little apostrophe next to it, which is read prime, E prime. You can see that together, the pink circle and the beige area fill up the entire rectangle. That is, together they compose the entire sample space. So the sum of the probability of event E and the probability of its complement is 1. Or rather, we can find the probability of an event happening if we simply subtract the probability of its complement from 1 or vice versa. We can find the probability of the complement if we subtract the probability of the event from 1. So for example, find the probability of randomly selecting a social networking site user who is not 25 to 34 years old. Okay, well, if I'm not in the group for 25 to 34 in this table, that means I'm in one of these other groups, 13 to 17, 18 to 24, 35 to 44, and so on. But instead of dealing with the hassle of adding up all the frequencies from the other age groups to figure out the probability, I can just use the complement rule of probability that the selected user is not in the age group from 25 to 34 is 1 minus the probability that he or she is in that age group. We know that the empirical probability of being in the age group of 25 to 34 is 765 divided by 3,000. That is the frequency of being in that age group divided by the total of the frequencies. So we simply use the complement rule and calculate 1 minus the value to find the probability of not being in that age group. 1 minus 765 over 3,000 gives us 0.745. I know this seems like a silly rule right now, but it will hold quite a bit of power later on. Okay, that's where we're going to end this one. I'll see you in the next video.